11.2, and this is all about radical functions. Now, this topic can be extremely complicated. What is a radical function? Well, if we just define it over here, we have some f of x is the nth root of some other function g of x. And that's, in general, a radical function, where g of x can be any function we have. This, if you looked at all the possibilities for g of x, it's extremely complicated. So we're going to have to narrow down the scope, and not too much, because, with calculus, we don't really consider a lot of these. We just look at the basic ones, so it's not going to hurt us too much. Even if we put in a polynomial, even if we limited g to be a polynomial, the end result, the picture of the graph of that function, can look crazy. Let's take a look at an example that I have in the textbook. So we're going to limit g to be polynomial, but we're going to actually limit it even further than just regular polynomials. We're just going to look at linear polynomials, because that'll get us through just about everything that we need. So, for example, if I take g to be some 9th degree polynomial that looks like this, its graph is unwieldy. We would not want to try and analyze this, even in the calculus with the techniques we have there. This would be a long and torturous problem. Now, you could analyze it in the calculus, and you could do that with the techniques provided, but we cannot analyze it here, other than just by looking at its graph. In the calculus, we could actually find some of these features and where these things are occurring, but we typically do not do something this complicated in the calculus. So we're going to avoid that. We're not going to be, if you will, looking at complications like this. Instead, what we're going to do is just put in essentially just a linear polynomial into our function. So that's what we're going to be analyzing now. So it makes life a lot easier, because obviously it would be kind of crazy if we tried to analyze something like that. So for us, g of x is just going to be some linear polynomial, so any sort of m times x plus b, or ax, a1x plus a0. If you want to write it in another form, you could say that, a1x plus a0, if you want to look at the polynomial notation we've given you. So that's where we're going to limit our g of x. Okay. N is any integer. N is any integer, so 2, 3, or higher, positive integer. If n is 2, that's a square root, and we don't write it. So this, you could write this, the square root, but typically we just write it in this form. We don't write the 2. If it's a 3, then it's a cube root. That's a cube root. And you can also write it in radical form, and you can also write it in exponent form. So that's the form that you want to do it. For us, we're just going to choose 2 and 3. Once in a while, you might see a 5th root or a 4th root, but very, very rarely. So we're going to focus our attention on more of what we will see rather than the potential of looking at this thing and blowing it up into a whole. You probably do a whole course in analyzing radical functions, but we're not. They're not as prevalent as you see in polynomials and what we'll see momentarily, our rational functions. Okay, so there are 2 types of problems we're going to be looking at then. They're going to either be the square root or the cube root of a linear polynomial. So we're going to either look at the square root of some, mx plus b. That's one type of problem. Or we'll look at the cube root of mx plus b. Now, in general, if we want to look at the square root with just an x, we always go back to the most fundamental type. So the most fundamental type is let b equal to 0 and m is equal to 1, and we consider our f of x equal to the square root of x. Now, in these problems, the first thing you're looking at is you want to find the domain. And when you're dealing with the square root, you have to make sure that you do not have a negative under the radical. It's also true if you're looking for a fourth root or a sixth root. Even roots cannot have a negative under the radical. So over here, we say the domain is the set of all elements x. That's it. X is a real number, and x has to be greater than or equal to. I can have 0 in that expression. Square root of 0 is just 0, but I can't have a negative value. Now, the graph of that, when I plug it into my calculator or my Desmos application, will look something like this. Again, x has to be 0 or positive, and it'll go up like this. It's really a parabola on its side, if you will. And that's what the graph of this basic function looks like. Now, what is the range of this? Well, it seems to be going, upward, but, it's kind of, looks like it might settle down to something, but it doesn't. The range of this function, set of all elements y, such that y, again, is also any real, but y can go from 0 to infinity. So y is simply greater than or equal to 0. And that's the range of that function. So if this is a square root, meaning an even root, we have some restrictions on the domain and the range. Let's take a look at the cube root over here. Let's say my f of x is equal to the cube root of x. Well, now I can have negatives under that radical, because it's possible. I can take the cube root of something, and I take the cube root of a negative, and I can get a negative. Like the cube root, for example, the cube root of -8 is a -2, where the square root of -4 I can't do. But I can put negatives under the radical if I have an odd exponent, index number there. So the domain for this set of all elements x, that said x is any real number. Can be anything. Now, if I were to plot that, I get something that looks like this. Plug it into your calculator, you'll see something that looks like this. And in this case, the range for this can also be any real number. So if it's an odd exponent or a cube root, we don't have to worry about what goes in and what comes out, because the range for this is the same sort of thing. Y, and y is just any real number. Any real number will do. Okay, so where it becomes problematic with radicals is with square roots. That's where we have to do extra work. For the cube roots, it doesn't matter what we put in here, the domain and range, it's still going to work. I could put in m being, a negative value, b being positive and negative. I don't have to worry. But where I do have to worry is the domain of the square root. So let's focus on that. So now this is the general one, and then we're going to come back to this picture in a minute. So let's now take a look and focus on our square root. And then we'll talk very quickly and briefly about the end behavior of these functions as well. So let's take a look at now square roots. Square roots and domain issues. So again, I'm going to look at, in general, something like this. The square root of some m times x plus b. So let's look at a specific example. F of x is equal to the square root of 2x minus 3. And I want to find the domain. I have to require that what's underneath the radical symbol, so this is over here, is our radical symbol. What's underneath here is called the radicand. So I have to require that the radicand has to be strictly, greater than or equal to 0. So to find the domain over here, I have to solve this inequality. I'm going to look at 2x minus 3 has to be greater than or equal to 0. So on the domain, we have to do a little extra work over here. So what would I do? I could add 3 to both sides. I get 2x is greater than or equal to 3. And divide both sides by 2. It's a positive, so I don't have to worry about anything. We'll talk about that in a second. So I get my final answer that x then has to be greater than or equal to 3/2. So for my domain for this function, very simply, I write the domain, set of all elements x. X is a real number, and x has to be greater than or equal to 1.5 or 3/2 or 1.5. Very simple. Now the range is the same, provided I have a positive number out here. If you put a negative in front, it flips it. We'll talk to that maybe a little bit. It's not that critical right now, but the range is just the same as it was previously. It's all real numbers that are greater than or equal to 0. But what if we look at a second example over here? What if I have something like this? Here's another example. Here's my f of x is the square root of 4 minus 5x. And now everything switches. Now, let me just do the graph here. I'll just do the graph quick so you can see it, and then I'll do a new one with it. Let's do the graph while we're here. I'll do it quickly and graph it just so you can see what it looks like. And you can just plug this in and you'll see what you get. So if you plug this into your calculator, you're going to go over here. It's going to be at 3/2, and it's going to kind of go up. It just shifted the other right down when you. That's what that B does. It shifts it down, and it goes looking like that. So that's the graph of that function. And you can just plug it into your calculator or Desmos. I just did it my head calculator just to give a general shape of that. Okay, now let's look at a second example that I put up there and analyze that in the same fashion. So here's our second problem. The square root of 4 subtracting 5x. Again, we want to address the domain right away. It's a square root. Doesn't matter with the cube root. Cube root, domain, and range is all real numbers. So what do I have? I have to make sure that what's under the radicand is, again, strictly positive. Okay, so let's go through and solve this. Let me just do it up here so I have a little extra space. I want to talk to some issues that some students have. There's many ways of solving this. I'm going to do it 2 different ways so you can see. One way is I could move the constant over by subtracting 4 from both sides. So I get a negative 5x is greater than or equal to a negative 4. Then what I need to do is I need to divide both sides by negative 5. But we recall that when we're dealing with an inequality and we divide both sides by a negative, we have to change the direction of the inequality. Now, why is that? Some people might ask. For example, we know that 2 is less than 3. But if I divided both sides by a negative 1, I get negative, if I didn't change it, I get negative 2 is less than negative 3, which is not correct. To keep that same sense, I have to change it to the opposite. That's why we do that. Okay. So now, when we do this, I get x over here is less than or equal to positive 4/5. So it has to be less than 4/5. Now, what's the other way? Well, the other way I could have done it is add 5x to both sides. This is going to avoid dividing by a negative and switching the inequality. And I get 4 is greater than or equal to a positive 5x. Then I divide both sides by 5. And I get 4/5 is greater than or equal to x. But I can read it in reverse order. This is 4/5 is greater than x, or x is less than or equal to 4/5. So this is equivalent to this definition over here. Keep the same sense passing to the x to get the same answer. So you just have to be careful when you're solving your inequalities here. Now, the graph of this is interesting as well. So let's just write the domain. So the domain here would be set of all elements x. X is some real number with the condition that x has to be less than or equal to 4/5. The range for this is, again, all real numbers greater than or equal to 0. But if I look at the graph of this, this is what I'm looking at. Now, notice it's going to the left. So let's put here's 0, and here's 1, and here's 2 out here. And if I take this sort of thing, the picture is going to look like this. Now, x goes to the left. Oh, excuse me. So here we have fifths. So here's my 4/5 right here. So this is where I start, but x goes less than that. It kind of goes up like this. Be a little rounder, I'm sure. Probably go up a little more steeply than this. That's probably close to what you'd see. This goes through 2 over here. Now, how do I know this goes through 2? Well, if I set x equal to 0 over here, I get the square root of 4, which is 2. But notice now it goes in the opposite direction. So if you have a negative in front of your x over here, instead of opening up towards the right, it will open up towards the left. The range, again, is still 0 to infinity. It's just now the domain can be some negative values. So you just have to be a little bit careful finding the domain range. But you will do this frequently in the calculus to find where these things are defined. What's the domain and the range. So again, we're back to some basic algebra, and you should be able to use that. Okay, let's now address the other question that we addressed with polynomials yesterday, and that's the end behavior of these functions. What is the end behavior? Meaning, as x gets very, very large in plus or minus direction. So let's take a look at the 2 of them separately, the 2 types separately, the square roots and the cube roots. An end behavior, that's when x is approaching either plus or minus infinity. What happens to f of x? What does f of x approach? Okay, so let's start with the square root. And let's consider our regular square root with just an x in the, if you will, argument of the function here, the radicand, if you will. Now, as x gets very large, that goes to infinity. What happens to my f of x? That also gets closer and closer to infinity, because we saw that in the graph over here. This will go up like that. So what happens, as x gets large, this goes to infinity, but at a slower rate, but it will still go to infinity, but at a slower rate. So they both go to infinity. Now, what happens is if I change this function? This is a standard one. What if I change this and now consider f of x is equal to the square root of, say, 2x, or x plus 5. So what would that look like? Well, if I looked at, again, as x goes to infinity, we want to find out what happens to f of x. If you look at the graph, it looks like this. That when that is 0, x is negative 5. So in this case, when I solve the inequality for the domain, x would be greater than or equal to a negative 5. And then over here, this would be like the square root of 5 over here, so it looks something like this. Okay. In this case, we also see that as x goes to infinity, this also goes to infinity. Now, the other thing that happens is, what if I looked at both of those graphs together? And I looked at the end behavior. So let's take a look at using this, and you'll kind of see that. We kind of use Desmos again for this. Okay, go back to Desmos. Let's change this up over here. And y equals square root of x, and y equals square root of x plus 5. Okay, so here we have both of our functions. But now let's take a look at what happens as x, again, x has to go to plus infinity. It can't go to minus infinity because it's not in the domain. The domain of this, it has to be greater than negative 5. The domain of the other one has to be greater than or equal to 0. But let's take a look and we'll change our settings over here. And let's the x-axis, let's make that go up to, say, 200. And then the y-axis, let that go up to, say, let's go up to, 50. What you see happening is the further out I go, it's indistinguishable between the two graphs. You see how they approach each other? Further and further out, you see very little distinction between the two curves. So what we're saying over here, very simply, is that the end behavior of this graph looks like that. So when x goes to infinity, this f of x goes to square root of x. You can ignore the constant. Goes to the square root of x, meaning they're approximately equal to each other. They're what we sometimes call asymptotically connected in that way. Meaning for large values of x, you can ignore the constant. Always going to be the case. It doesn't matter what. Now, for example, however, now if I put in for, say, this other example, this is one example. Here's a second example. Let's take a look at a third example. Say that f of x is equal to the square root of, say, 2x plus 5. Again, we can see this is going to require that x is going to be greater than or equal to negative 2.5 or 5/2, so it's going to do that. But let's see what happens as x approaches infinity. What does f of x get closer to? Well, we're going to see that you can simply ignore the 5. You can't ignore the 2, and you're going to see this is going to get closer and closer. It's going to go to infinity, but how it goes to infinity is it's going to follow the following. It's going to be approximately equal to the square root of 2 times x. And we can show that again using decimals. So essentially, you ignore the constants in the argument or the radicand of that function. Let's just kind of show you that just to validate what we're looking at. So say, for example, I had 2x over here, and I put in 2x plus 5. Again, you can see they end up being indistinguishable from each other. Whereas down here, there is a big difference. Right at the origin, this is minus 2.5, and that's at 0. Here there's a difference, but in the end behavior, when x gets very large, there's no difference. So where does this come up? Where does this come up in the real world? Well, in the real world, in the engineering world, sometimes you have radicals, and they have a constant. What you can do is you can simplify it by taking an approximation and getting rid of the constants and just replacing with this. And that becomes very critical and very important for making some simplifications so you can solve problems. So over here you can see the end behavior. F will still go to infinity, but it goes to infinity in this form as opposed to that form. So in general, if I take my square root, my general square root with my linear function, linear polynomial function. So in general, if f of x is the square root of m times x plus b, as x goes to infinity, f of x looks more and more like the square of m times x, which also goes to infinity, but in this very distinct way. That's the end behavior for a square root. Now, if m happens to be, negative, then x has to go to minus infinity. Let me just show you that. For example, let's show what happens for another possible case. So let's take a look at f of x is equal to the square root of 3, and we're going to be subtracting, in this case, 2x. In this case, if I look at my domain over here, this is the graph of this function. It's going to look like this. It goes to 3 halves, x is a positive 3 halves. So it looks like this. Here's 1 and there's 2. So it goes right between there, and it looks like this. We're going to see the domain x has to be less than. So in this case, we would be looking at x going to negative infinity, not positive infinity like we looked at on the other ones. And what happens? Well, the f of x, that's going to look more like the square root of negative 2x. Now, this is only going to apply, obviously, here it's undefined. That's only going to be defined when x is out there. And you'll see that will work out because it'll give me that negative 2x. So when it's negative, it's not going to give me anything. We'll show that on Desmos here. Now, the result of this also goes to positive infinity along the y-axis. And let's just show you that. So whether I'm going to plus or minus infinity depends upon the radical, the argument of that square root function. Let's just show that again just so you can see what I'm talking about here to clarify that. So over here, I have my 3, well, I'll put a minus 2x over here, and then I'll put my 3 minus 2x. Now, this side, I don't have anything because it's going on the other side. So what do I have to do? I have to change this around. And we can let this go from, say, 0 to negative 300 or something like that. And let's kind of take a look at it over here. So there it is over here. When I put in those values, it's okay. This is my math there, and here's the other one. But again, as x goes to now negative infinity, the two functions become indistinguishable from each other. There is no difference in them. So they're identical for large values. So we use that from time to time. Let me see who's chiming in over here. Yes, Kristen. A question there?
Yeah, sorry, I was on mute. This might seem kind of a silly question, but just to clarify, because the radicand can never be negative, we would say f of x can never approach positive, or I'm sorry, negative infinity, right, in a square root?
Well, it can it can approach negative infinity if there's a negative coefficient in front of that. You see that?
Okay.
But if I look at the other case, for example, for this one, it can only go to positive infinity. However, for this one, it can only go to negative infinity, because that negative is going to turn it into a positive. The graph of this looks like that. The graph of this looks like that.
Right, but when we say like as f approaches negative infinity, for instance, in this example, f of x approaches square root of negative 2x approaches infinity, it would never be.
For this one, I can't go to positive infinity.
Right.
This one, it's not possible.
Right.
In this one, I can't go to negative infinity. So this one, I can't go to positive infinity, and this one, I can't go to negative infinity. It's either one or the other, not both.
Got it.
As opposed to the next thing we'll look at, the cube root. And let's take a look at the end behavior of the cube root now. Now, this does become important when you analyze certain problems in the sciences and engineering, because sometimes you get rid of all the constants and say, well, for large x, I can ignore the constants, and then you just get a square root, and then you can manipulate it by squaring it and make your analysis so much easier. It's not exact, but it's pretty close the larger x becomes. But now let's take a look at the cube root. That's a lot different and a lot easier to deal with. Say, for example, I have f of x equal to the cube root of x. Again, its graph looks like this. This case, I don't care what the sign is under the radical. So I have two cases. I can look at what happens as x goes to plus infinity. My f of x, in this case, will go to positive infinity. But I can also consider the case, unlike the square root, of x going to negative infinity. Now I'm going backwards. F of x goes to negative infinity as well. So unlike the square root, I can have different signs of positive or negative under the radical, and it works out okay. Now, what happens if I look at some examples that are modifications of that? In more general case, so in general, we're looking at something like this. F of x is the cube root of some m times plus b, where m can be positive or negative, and b can be positive or negative, whatever the case. So let's take a look at some examples. Say, for example, f of x is the cube root of 3x minus 1. Well, what would that look? First off, we can see that the domain is all real numbers, the range is all real numbers. When I look at the graph of this, this is just going to shift a little bit on the x-axis, you'll see. So let's go right to the graph. I'm going to do it by hand here. It's a little bit easier to do that. put 1 over here and then 2 over here. So what this is going to look like, it's going to have the same shape, but it's going to be shifted down 1/3 when that goes to 0. When x is 1/3, I get a 0. So right here, I'm do it in blue, that's the 1/3. So it's going to look similar to this, but just going to be shifted down. We'll show that on Desmos momentarily. Now in this case, as x goes to infinity, that will also go to infinity. So over here, as x goes to infinity, f of x will also get closer to infinity, but at a slower rate, you know. And x can also go to negative infinity in this example, and the f of x would also go to negative infinity. Now, what would happen is, as x got very large, I could ignore that -1. So in this case, in both cases, plus or minus infinity, as x goes to either plus or minus, f of x my microphone, oh, it's coming back. I'll let everyone reconnect. So what happened here, Blackboard just kind of did some strange things. But I think everyone should be back. There's still one more Tyler as we're still reconnecting. Are we okay? Can you see the screen again? We're going to talk about what I was doing over here. So in this case, we can have x going to either plus or minus infinity, and f of x, in this case, it's plus infinity, goes to plus infinity, x goes to negative infinity, y goes to negative infinity. Or plus or minus, I just can look at the radicand without the constant. Let's plug that into Desmos so we can see that same sort of feature. Okay, hopefully we're back up and running okay. Let's go to change this now. Here I'm going to use an n root, so let's kind of do that. Y equal to, here they got a nice little keypad over here, and I think they have for the other functions over here, and it's miscellaneous. I think it might be miscellaneous. Here it has the n root over here. So I can now plug in a 3 for the cube root, and let's plug in what I have over there, the 3x and then the 3x minus 1. Okay, now let's kind of plug in something a little more reasonable so we can kind of see everything here. Now, you can see here that they're virtually indistinguishable from each other. Where it really matters is right in here. So as x gets either large positive or large negative, the red and the blue are on top of each other. Where it's different is a little bit over here. The green has that shifting that I talked about. So let's take a look at that on the x-axis. Let's go from, say, -5 to 5. And then you'll see that little shifting I was talking about. So there it is. This one goes out, 0.333, as I said, 1/3. It just shifts the other one down 1/3. But, and you can see not too far away from that, they become indistinguishable. So that approximation is pretty good, even when, x is out here at 3. It's a pretty good approximation, reasonable approximation. So that's all I wanted to kind of talk to and address here. Now we could also do this on the TI calculator, but it's a lot more complicated. This is much more powerful as a tool for analyzing things, and that's why I'm kind of emphasizing it more than anything else. But again, you can ignore this. Now, what happens if the m is negative? Let's take a look at that. Let's stay with the cube root. But now, let's take a look at this. What happens if I take f of x equal to the cube root of negative x? And then I'll look at more generally. Well, what happens here? What does the graph look like? Well, the graph changes a little bit now. Where initially, remember when it was a positive x, I went here and then up. Now you're going to find it's going to actually do the opposite. That's what the graph is going to look like. So in this case now, as x goes to plus infinity, your f of x goes to negative infinity. Or as x goes to negative infinity, so I'm going negative infinity, my f of x now is positive. F of x goes to positive infinity. And let's say I took a look at another example of that. And say I took a f of x equal to the cube root of 5 subtracting x. And let's plug both of those in to Desmos and indeed see this behavior that's happening that I've indicated there. So over here, I'm saying minus x for this one. And this is going to be a 5 minus x. Okay, now you can kind of see, let me just move it down so you can kind of see what happens. What that minus 5 did, it just shifted it down from the red to this other one. And let me kind of now show what happens as x gets large. We won't make y to be so large. Let's go from minus 10 to say 10. And let x now be very large. So say, minus 50 to say 50. In fact, let's go a little bit further. Let's go to 250. 250. And you can kind of see what happens. There's a shift here, but as you go further and further out, they line up with each other, and they just fall on top of each other. So asymptotically, we have the connection, or as x goes to plus or minus infinity, what you see over here now is you have that, so as x goes to plus or minus infinity, the f of x, that will go to the cube root of the negative of x. So you just, for the odd index over here, you don't have to worry. You can go to plus or minus. Only for the square root do you have problems. Okay, that's all we want to kind of give you, some of that feeling for how radicals behave. Now, it gets much more complicated if I put a quadratic or a cubic, as you saw from the other ones. However, the end behavior is actually easier when you're dealing with polynomials.